have, and you can find him all over the place. So I first met Tony about 10 years ago when he was working with a company called ESAB, which you will all know, and based in Charlotte in the USA. And I went there to see him because he was one of my members and of TWI. And it was great because I realized quite quickly that he actually understood things like cricket was not just the name for an insect. And he also knew McVitie's digestive biscuits are the best to have with a cup of tea. So that's when I realized he was actually one of my own kind. And I'm pleased to say that Tony emanates from the UK, although he's a very international person. So it was great when he actually left ESAB, and I thought that was the end of our collaboration. However, Miller in Appleton then became members of TWI. So I've been able to see Tony regularly, and it's been a pleasure to learn from him about something that I already thought I knew. Tony is basically global director for aluminium for Miller and ITW, but his reach is far more outside Miller than you may think. So he's got an incredibly deep track record in aluminium, going way back to things like his role in South Africa for the Welding Institute there, right up to the present time when he influences committees on things like AWS in the United States. So Tony is probably one of the few guys who actually, when you pick up a reference to how you're going to put aluminium together, he's probably had some kind of influence on that. He's also an advocate for how to get the best out of aluminium, and I'm sure you'll learn today. There are tricks on the trade, and there's tricks about aluminium that actually present problems often, but there are also opportunities to actually gain the advantages of that metal and its alloys. Tony's co-authored or he's authored many informative books, publications, workshops, training, and you can find all these mainly available through the associations or even on the internet. And he also supports TWI, so he's a strong supporter of the TWI library, and he helps us get proper information about aluminium and welding. In his committee work, he's basically, I don't think I've met anybody who's so much an encyclopedia of codes, standards, practices, material selection, and actually the outcomes of using these materials. So hopefully you're going to learn some of that today from Tony. And then finally, he's also one of the best experts I know at cooking those great big American steaks that you put on the barbecue. And, you know, it's a recurring dream I've had all year is to actually see him do that again in person and taste the results of it. I think he's been practicing with veggie burgers, by the way, so may have a new skill. So it's a real pleasure to introduce him to you, and I hope you have an interesting and enjoyable webinar. And I also would like to thank Tony for getting up early and to looking so awake for us, Tony. And over to you, and thank you again.
All right. Great. Thanks, Chris.
All right, Tony, I'm going to make you the host again, so you'll be able to
just share my screen.
Yes, now you should be able to share your screen.
Yeah, it's visible now.
You see it?
Yes, sir.
Yeah.
Thank you.
Okay. All right. Well, thanks for all that, guys. This talk, we have a limited amount of time, so this is certainly an overview. We don't have time to get into real depth in most of this information that we're going to be looking at right now. But my hope is that you will see the areas that I consider to be most important related to the joining of aluminum and aluminum alloys. and give you an idea of areas within each of those areas, if you like, that we probably could expand upon. And then I'll also include some information on other materials where you can actually gain more information on all these topics. So anyway, let's get into it. But remember, this is an overview, and it's quite a lengthy presentation, so I'm going to be moving through it at a reasonable pace. As Chris said, that's me. I'm involved with a lot of AWS work. I've been on the AWS board now as a director at large for the last 10 years, actually. But I work with the AWS a lot. I work with ASME a little. So that's kind of my background. Sorry, jumping too fast here. So what we're going to talk about here, I've listed the subjects that we're going to address. First of all, we're going to look at trends in aluminum usage. In other words, where are we seeing aluminum being used now, and why are we seeing aluminum, and typically more aluminum being used in those areas? Then we're going to look at a little bit about the material itself, say about the metal. What is aluminum? You know, how many types of aluminum are there? How do we recognize the different types? So well, there's a section on that. Then filler metal selection. Now, I chose filler metal selection because it's something that's very different than other materials. There are a lot of considerations when you select a filler material for aluminum that you don't necessarily need to consider when you select a filler alloy for most other materials. So we'll look at that and again give you an overview of how filler metal selection works, so you might appreciate it and dig deeper. Okay, then weld discontinuities. There are a couple of discontinuities that are pretty specific to aluminum, and one of them you'll all know, I'm sure, if you've worked with aluminum, is porosity. It's always an issue. It raises its head continuously. So I'm going to look a little bit at porosity, what it is, where it comes from, and how we might prevent it. And the other one is hot cracking, solidification cracking. A lot of the aluminum alloys are very solidification crack sensitive. And I want to explain why that is and how a welding engineer can design his welding procedures and filler alloy selection to combat hot cracking issues. Okay. And then the last section is going to be technical publications. As I said earlier, I'm going to go through a list of, I don't know, maybe 6, 8, 9, 10 publications that I consider to be very useful if you want to learn more about this particular subject. Okay, let's move on. All right, trends for aluminum demand. I've got a list here that I use all the time to tell people why I think we're seeing more and more aluminum out there in the industry. And some of them are really obvious. And the top one, obviously, is probably the biggest reason why we're seeing more aluminum. That's because it weighs 1/3 that of steel. And there are many industries out there now, particularly the transportation industry, that are trying to lightweight. They're trying to make things lighter and lighter, and it's all about fuel efficiency. So that is by far the most driving force in the increased use of aluminum alloys. In terms of the material itself, it has a wide range of strength. So we have a great selection of different alloys that might fit different applications. We get some of the very low strength alloys like the 1000 series, the commercially pure aluminums, which are typically not used in structural applications, but they're used for other reasons like electrical conductivity and corrosion resistance. But they don't have very great strength. But then at the other end of the range, we have some of the alloys, particularly the heat treatable alloys, that get in excess of 90 KSI. So some of the materials that are used in the aerospace industry, the 2000 series and the 7000 series, that's the copper-based alloys and the zinc-based alloys, have great strength in certain heat-treated conditions, in certain tempers. So there's a wide selection in terms of design criteria. High electrical conductivity, 60% of copper. So it has really good electrical conductivity, and it is used for that property in some applications. It's far cheaper than copper, and it's much lighter, obviously, than copper. So it can be used as an electrical conductivity media quite successfully. High thermal conductivity, 5 times that of steel. So it conducts heat 5 times faster than steel. Is that a good thing? Yeah, possibly, if you're using it as a heat sink or something like that. But the main consideration there is when we weld it. When we try to weld aluminum, the heat is being pulled away 5 times faster than when we weld steel. So is that a consideration when we design our procedures and we choose our welding equipment? Absolutely. Yes, it is. They talk about welding aluminum hot and fast, and that's what it's all about. You need high current densities, and you need fast travel speeds to prevent lack of fusion. Okay, good corrosion resistance, absolutely. But why does it have good corrosion resistance? It's because it has an adherent oxide. And aluminum oxide is a strange animal. It has some weird characteristics, one of which is that it melts at 3 times the temperature of aluminum. So aluminum melts around 1200 degrees, aluminum oxide 3600 degrees. So yeah, is that an issue? Well, yes, certainly can be, because it can act as an insulator when we try to weld. So we need to address that when we pre-clean and prepare for welding, most certainly. Aluminum is resistant to many chemicals. There are certain aluminum alloys that are made of high purity specifically for chemical storage. So yeah, we can find some alloys that are used just for chemical storage. Has no ductile to brittle transition. That's an interesting one, right? Aluminum, as we drop the temperature and the temperature goes lower and lower and lower, it actually, its mechanical properties actually increase. Its tensile strength goes up, and its toughness actually gets better. So it is a really good material to use in cryogenic applications. This is why we see it being used for LNG tankers and such like. Toughness, pound for pound, will absorb twice the crash energy than typical automotive steel. The automotive industry here in the States has been working and testing aluminum to prove it for many years now. And there are many studies that show if you design the component correctly with crash zones, a vehicle can withstand a heck of a lot more, can absorb a heck of a lot more energy than it would with steel. So so it has advantages in those directions. It's weldable and workable, absolutely. If we understand it, it's easy to work with. Problem is, a lot of people don't understand it and they treat it like steel and they run into problems. It is different. It just needs to be addressed differently. It's easily extruded. We see lots and lots of extruded aluminum out there in the field. And that is that's a really good advantage when we plan fabrication. We can make extruded components that assist with assembly. We can build in weld preps as part of the extruded part. There's all kinds of clever things we can do in design when we use extrusions. Priced by the pound and used by the foot. Okay, people often say, well, I'd love to use aluminum, but it costs more than steel. But hey, you're only going to use 1/3, right? And it's priced by the pound, not by the foot. So it is often a good choice to replace steel. And another one that's really important is it can be recycled extremely efficiently. It costs a fraction to recycle aluminum compared to actually making aluminum from scratch. So yeah, it recycles very efficiently. Usage. This is a graph that I got from the Aluminum Association some time ago, but it's actual and predicted usage. And this is world per person demand for aluminum. And we can see from 1960s going through to the 2020, it's on an upward climb, and both predictions and actual are very, very similar. Now, I had a chart that went back to 1940, and this curve wandered all the way down to nearly zero in 1940. There was very little aluminum being used, and something happened in the early 1940s that made aluminum much more attractive for welding fabrication. And some of you probably know that was the introduction of the heliarc welding process, or the TIG, or gas tungsten arc welding as we know it now, was developed in the early 1940s. And what that did shortly after that, of course, we got MIG, or the gas metal arc welding process. But the inert welding processes were the big breakthrough in welding aluminum. Up until then, it was very difficult. You needed fluxes that were very corrosive. Typically, it was welded with oxyacetylene. You could only weld certain alloys. It was very, very difficult. So yeah, absolutely, the introduction of the inert gas welding processes in the 1940s was a massive breakthrough. And from then on, we've just been seeing more and more aluminum. I'll just go through a few pictures here that I chose of different applications, and just look at them quickly. First of all, okay, this again is related to the automotive industry, and these are figures related to lightweighting vehicles. And as you can see, from 1975 to the 2020s, it just continues to grow. The amount of aluminum that's going into vehicles, as I said earlier, is just increasing continually. It's all about fuel efficiency. Okay. Fuel efficiency. They're trying to increase fuel efficiency enormously over the next few years. They're not expecting the price of gas to go down. Some of the vehicles, and you've all seen these, the Land Rover, the Mercedes, these guys have been using aluminum for a long time. BMW, Audi were one of the pioneers in the space frame development when they started using aluminum in vehicles. The big one over here a few years back was the F-150, the Ford F-150, which is the best-selling vehicle probably in the world, but certainly in the States. It became an aluminum-intensive body, and it was a big deal at the time. And as you can see there, first high-volume aluminum bodied vehicle to go into production in the world. About 850,000 trucks per year and 350,000 tons of aluminum sheet per annum. So that was a big deal. I'll tell you a quick story here. I have a good friend who I've known for many years, a lady called Joanne, and she works for Ford, and she heads up one of the research groups, PhD in laser welding. That was a specialty. I've worked with her on and off for years. Her and her husband, who also works in the automotive industry, developing aluminum fasteners, were working on this F-150 as a top secret project. They were sworn to secrecy. They didn't want the competitors to know that they were putting all this aluminum into the vehicle. And they come to find out that their daughter, who was very young at the time, told a teacher and her classmates that her mother and dad were working on an aluminum F-150. So it was kind of yeah. That was, yeah, these big secrets, right? Okay, aluminum engine's been around a long time. First aircraft would probably have never gotten off the ground without aluminum, lightweight. Yeah, we all know. And that's an Audi, I'm pretty sure, what they call the space frame. One of the first developments in aluminum-bodied vehicles. Extrusions, these are all 6000 series, typically extruded tubing, welded with TIG. Closer view, you can see the arc etching at the side of the welds there. When you're welding aluminum with TIG, you get well, it's typically AC, you get a cleaning action that strips the oxide during the welding process. And you can see that at the side of the welder. Nice welds. High performance application here. I'm not sure about India, whether you guys are using these high speed trains, probably, but certainly Japan and a lot of other countries out there in Europe are using these, and they're very aluminum intensive and very high performance. So I've been specializing in aluminum now for over 25 years. And I remember the shift, right, when I started, the shift from sort of mundane components being welded, like radiators for trucks and things, to high performance components like drive shafts and components like this. And all of a sudden you've got high integrity welds that need to perform in service. So the integrity becomes more and more critical, obviously. This very common sight in the States now, aluminum truck trailers, lightweighting again is becoming pretty much mandatory. And this is an older application, but still used extensively, heat exchangers, radiators, and all kinds of heat exchangers. Typically use the 3000 series aluminum manganese alloys, welded with the 4000 series filler alloys, so silicon alloys. Yeah. More extrusions. Very common over here in the States, these toolboxes, all aluminum. Watercraft. These are smaller bolts made of 5000 series, some 6000 series extrusions, but 5000 series plate. Sometimes low mag, 5052, which is about 2.5% magnesium. Not terribly high strength, but suitable for lower strength applications like this. These are not high performance as such, a smaller craft. Might use 5086, which is a bit higher strength. Let me get this. This is more of a high performance, what we would refer to as a work boat. This is a Coast Guard, as you can see. Pretty much all aluminum, lightweight, travel extremely fast. Military vessels. This is a hovercraft, very high performance. Went through a lot of learning curves with these vessels many years ago. Again, when I first got into aluminum, they were using some alloys that they didn't realize were not terribly suited for marine applications, and they were having corrosion problems. Since then, there have been standards produced to govern the manufacture of both certainly the base materials, to make sure that they will withstand marine applications in certain tempers. But also the filler alloy companies have become aware of the chemistries of some of the filler alloys that need to operate in these environments are critical. It's not just strength. You have to look at corrosion as well. And the amounts of magnesium and manganese in these high strength 5000 series filler alloys are very important in terms of will they stand up in this sort of environment. Very large ships, military ships typically, but also commercial, car ferries and things like that. This is a vessel that was built by Incat in Tasmania. I actually went to visit these guys and had an opportunity to go on one of these in Tasmania at their shipyard. Very, very impressive, massive vessels. There were 3 of them built for the US military a number of years back. That's the same vessel. Travel at incredible speeds because they're so light. And you notice they're not painted. This one is not painted. And I asked the design engineer at Incat, what was that all about? And he said, well, why add all that weight? And he told me how much the paint weighs to paint a vessel like this. He said, what's the point? It's not going to rust, right? It's aluminum. So yeah, quite impressive. And here we see a Cryogenic application. These are very large aluminum spheres, 4 aluminum spheres on this vessel, 1, 2, 3, 4, and they're made of aluminum up to, they tell me, up to about 8 inches thick in some sections. So they're very large vessels for the storage of liquid natural gas and the transportation of liquid natural gas. Cryogenic application. Aluminum works real well. Okay, let's look a little bit at the material itself. Again, remember, this is an overview. We haven't got the time to get into great depth, but it should give you a decent overview of the different types of materials. First of all, we'll talk about the strengthening of aluminum. Aluminum itself, pure aluminum, has very low strength, as I said earlier, about 10 KSI. So not terribly useful for structural applications. So one of the first things they did after coming up with a viable method of extracting the aluminum metal from the ore was to figure out how they could make it stronger. They knew it had great corrosion resistance, it was lightweight, but didn't have great strength. So they found by adding alloying elements to the aluminum, we could increase its strength substantially. One of the first ones were the 2000 series, the copper alloys. Duralumin is a name that some of you may have heard. It's one of the early aluminum copper alloys, and everybody used to say it was unweldable, and it was pretty close to being because of the level of copper in the alloy that they put in to strengthen it. They didn't realize how it was going to affect the crack sensitivity. But since then, they've come up with 2000 series copper-based alloys that are weldable and are very, very strong and are used in things like the aerospace and aircraft industry. So alloying was the first idea, and it worked, and lots of different alloying elements can be added to aluminum to give it strength in different ways. The second method is, once we've added these alloying elements, some of these materials lend themselves to strain hardening extremely well. The 5000 series, the aluminum magnesium alloys, for instance, strain harden extremely efficiently. And so we'll talk a little bit about how that works. And then the third method of strengthening is heat treatment. Typically, solutionizing and precipitation hardening, and referred to as solution heat treatment and artificial age, is the method of giving the heat treatable alloys its highest strength. And we'll talk a little bit about that. And as I say, a little bit, this is an overview, remember. Right. Good example here, I believe, of how we can add alloying elements to aluminum and give it extra strength. So I've chosen, what, 5 different 5000 series alloys. The 5000, just now we're going to talk about the alloy system. Any alloy beginning with a 5, referred to as the 5000 series, is a magnesium alloy. It means magnesium is the primary alloying element in any of these 5s. Okay, and here we have an alloy called 5005, and it has less than 1% magnesium, and its strength is around here. As we increase the aluminum, we go to 2.5%, we get 5052, which is a very popular alloy. You use it for fuel tanks. It's very formable because it has relatively low strength and great ductility. And it runs in about here. And then we can add more magnesium and we get 5454 with slightly more strength. Then actually that needs to come down a bit, and it needs to go over here a bit. But anyway, I'll have to fix that slide. But the example is good. It's a good representation. We've got 5086 here with slightly more mag, slightly more strength. 5083, slightly more strength, slightly more mag. So we can see as we add more and more magnesium, we get more and more strength. So that to me is a pretty good example on how alloying assists in strengthening certain alloys. This is a non-heat treatable alloy. It will not respond to heat treatment in terms of strengthening. If we heat it to a high temperature, we will anneal it, we'll drop it to its lowest strength. But other than that, we cannot increase its strength by thermal treatment, just strain hardening, okay? So what is strain hardening? So we take a 5000 series or any of the non-heat treatable alloys, or even the heat treatable alloys for that matter. We can strain harden them all. They all will respond to strain hardening. Well, this example is a 5052, which is a 2.5% magnesium. And it's in an O temper. See, 5052-O, that means that's the annealed strength. The O means that it's annealed. The annealed strength of any aluminum alloy is its lowest strength. Sometimes people call it dead soft condition. Right, so in this case, we take a 1-inch plate of 5052 and its lowest strength, and its minimum tensile strength is guaranteed to be 28 KSI. All right, so now we put that plate, a 1-inch plate, through a set of rolls, and we reduce its cross-sectional area by 75%. We take it down a 1/4 inch. All right, we have now strain hardened that material to a H38 temper. All right, and we've increased its strength from 28 KSI to 42 KSI. Okay. We see its yield strength also is increased significantly, and its ductility is reduced as we would expect, right? Tensile strength's gone up, elongation has gone down. Right, so what does all that mean? What have we actually done there? Let me go, yeah. Okay. All right, so no, let's go back. So what we've actually done here is we have taken the grain structure of the material and we have compressed it and we've elongated the grains of the material, and we've also added residual stress to the internal structure of the plate because of this deformation. And this results in this increase in strength, right? So now we've got preferential grain structure, we've got internal stress within the material, all of which lends itself to increasing the strength. All right. So what actually happens when we weld this material in that strain hardened condition? All right. Well, the temperature of the weld in the heat affected zone is such that it will return the material to its annealed strength, right? It will no longer have that high strength. The rest of the material will, it's unaffected, but the heat affected zone will return to the annealed condition. That is unavoidable, cannot be helped. The good thing is that it's predictable. We know exactly what it's going to be, so we can design around that strength. And it isn't dramatic in the non-heat treatable alloys. It's substantial, but not as bad as it could be in the heat treatable alloys. And we know what it is, exactly what it is, so we can make our design around that strength. Okay. This is what actually happens. This is what the grain structure of the O temper, the annealed, looks like. This is as we start doing more and more strain hardening, right? Cold working, it's addressed as here, same difference. Strain hardening, cold working. This is taking it to a H14, which is elongating the grain slightly, and this is taking it to an 8, which is the maximum strength, which is elongating the material dramatically. But when we weld it, we take this material here and we take it back to the anneal strength here, like that, the O temper. Okay. Okay, so that's the non-heat treatable alloys we've just looked at. Now let's take a look at the heat treatable alloys. Now how are their strength is increased through thermal treatment, and this is a typical, one of the most common materials out there in the terms of heat treatable alloys is 6061. It's used all the time, and this is why I chose it as an example. If we take a piece of 6061 in the O temper, which is the dead soft condition, its tensile strength is 18 KSI. All right. If we take that material and we heat it up to 990 degrees and then quench it in water, we change its temper from -0 to T4. The T4 temper is solution heat treated only. And we increase the strength by doing that from 18 KSI to 30 KSI. So we've heated the material to 990, quenched it in water, and increased the strength substantially. You know, what's that all about? Well, this material has small amounts of magnesium and silicon, When we heat this material to these temperatures, the magnesium and the silicon combined and form magnesium silicide, compound called magnesium silicide, which is taken into solution at this temperature. When we quench it, we trap it in solution, right, which gives it strength. Now, is this the best strength, and is the mechanical properties great in this condition? No, they're not. So then we take the material in the T4 condition and we heat it up to around 350 degrees Fahrenheit. These are Fahrenheit, by the way, guys, for 10 to 12 hours. And what does that do? That slowly precipitates the mag silicide out of solution, and it gives us our optimum strength. So there are strength curves which show you time at temperature and how you can precipitate the mag silicide out of solution to get the optimum strength. And for this material, about 10 to 12 hours at 350 is about the optimum. That's what's used in industry to produce a T6 temper. People out there buy this material day in and day out in the T6 condition. 6061 T6 is probably one of the most popular materials used out there in the form of extrusions. And it has a guaranteed minimum tensile strength of 42 KSI, as opposed to the annealed condition, which is 18, all right? So we more than double the strength of the material by putting it through this heat treatment. But now you look at this heat treatment, it's pretty complex, right? They spend a lot of time getting this T6 condition into this material. So what happens when we weld it? What happens when we weld 6061 T6? Well, we really screw up the heat affected zone. This section here, well, actually D, the heat affected zone, we partially anneal it and overage it. We further precipitate the mag silicide, which weakens it, and we move it closer to its anneal strength. Now, the amount we do that is dependent on the heat input during the welding process. So this is very different than the non-heat treatables. The non-heat treatable, it doesn't matter how hot you get them, you always anneal the heat affected zone. The heat treatables, absolutely. The higher you get these, the higher the temperature in the heat affected zone during welding, the lower the strength in the transverse condition. So when people fail welding procedure qualification tests with the 6000 series, right, on their transverse tensile tests, the reason is just about always that they are overheating the base material during the welding process, right? So the rule here is to keep the heat down as low as possible if you want to get the best strength out of the base material after it's been welded. So stringer passes, don't weave, fast stringer passes, low heat input, watch the interpass temperature and preheat. Don't preheat really if you can avoid it, and you usually can. You don't need to preheat aluminum. That's a fallacy. Some people tell you you've got to preheat it. That's nonsense. The only purpose preheat serves, as far as I'm concerned, is to draw away moisture, because it certainly doesn't help with regard to heat sink. You need high current density to do that. So yeah, so that's one of the issues we have with welding the heat treatable alloys. Okay, a little bit about the alloys themselves and how they're identified. This is what is referred to as the teal sheets. And if you go to the Aluminum Association website, www.aluminum.org, you can find that as a free download if you dig deep enough. Always has been, I'm pretty sure it still is. And what this is a record of all the raw materials that are registered with the Aluminum Association. This is an international alloy designation system document. So it's recognized internationally. There is an international accord. There are, I can't remember the latest number, probably about 600 or 700 different aluminum alloys listed in the teal sheets. And every one of them has its chemical composition. So you will realize just now when we talk about cracking, If you don't understand the chemical composition of the alloy you're welding, it's the blind leading the blind. You can't determine how to weld it. You can't even determine whether it's weldable, because there are some aluminum alloys out there that cannot be welded without cracking. And it's because of the chemistry. So any welding engineer who wants to design welding procedures really finds this document useful if he comes across an aluminum alloy that he doesn't recognize and he hasn't worked with many times. He can go straight to this document, find the chemistry of that alloy, and determine through its chemistry, is it first weldable? And if it is, how should I weld it? What is the best filler alloy to match the base material? Or not even match it, maybe to use with a different chemistry to prevent hot cracking. So this is a very useful document, guys. And it is a free download, as I said, if you don't have it already. All right, so this is wrought material. We're going to talk about wrought. What is wrought material? Well, the easiest way to describe wrought material is, for me anyway, is anything except a casting. As sheet, plate, foil, extrusion, wire, rod, bar, forging, and so forth. Anything other than a casting is classified as a wrought material. So all those materials are listed in that book. All right, so I already mentioned there are two types of aluminum alloys. There's the heat treatable and the non-heat treatable. And I've already mentioned that we talk about the 2000, 1000, and so on. So the 2000, 6000, 7000 are heat treatable. And the 1, 3, and 5, and most of the 4000 are non-heat treatable. And I say most because there are a couple of 4000 that are heat treatable, because this is the silicon alloys, primary alloying element silicon, but some of them have little bits of copper or magnesium added, which turns them from a non-heat treatable to a heat treatable. That's another story. Okay. So we got heat treatable, non-heat treatable. So how does all that work? All right. So how do these numbers work? So first of all, it's a 4-digit numbering system, and you can see here, these are typical numbers used for alloy identification. Some of these you'll recognize, 4043, I'm sure. 5052 we mentioned. 4943 is a relatively new filler alloy that has higher strength than 4043, and so on. Right, so the first digit in the alloy designation system, as I've already mentioned, indicates the principal alloying element of that aluminum alloy. And here they are. The 1000 series, commercially pure aluminum, 99% minimum, pure. What is it used for? Electrical conductivity and corrosion resistance, actually. 2000 series, copper. What's its characteristic? Strength, high strength, heat treatable. Incidentally, all the blue ones are heat treatable and the orange ones are non-heat treatable. 3000 series, manganese. Thermal conductivity is really good. It has the highest thermal conductivity after the 1000 series, and it's used for things like pots and pans. The old aluminum pots and pans were all made of 3000 series. Radiators and heat exchangers, because of its good thermal conductivity and relatively moderate strength, use the 3000 series. 4000 series, silicon. Where do we see them? Filler alloys. Why? Reduced shrinkage. Silicon has some really strange characteristics when it's in aluminum. One of them is that it actually expands when the material solidifies rather than contracts. So it is a really good element to have in a filler alloy to prevent hot cracking. So some of the lowest crack sensitive materials out there are 4000 series. 5000 series, magnesium. This is the workhorse. Welded strength, has good welded strength. It's a strain hardened material, but it still keeps its strength pretty good even after welding. Used in many, many applications. 6000 series, magnesium and silicon, right, which form magnesium silicide, remember, heat treatable. It's used as extrusions primarily because of its strength and its flexibility. It can extrude really, really well. Why? Why do we not see 5,000 series extrusions? Because it's strain hardened so fast, it's really, really difficult to extrude 5,000 series. It can be done, but it's very, very slow and it's very, very expensive. So you don't see them often. They're custom made usually. 6,000, I'll guarantee you, you go in any store and you buy an aluminum extrusion, it's going to be a 6,000 series. 7,000 series, high strength to weight ratio, aerospace stuff, or high performance sporting equipment. These are the zinc alloys. 7,000 series aluminum with zinc. Okay, you can ignore the 8 and 9. I don't even know why they're there. Excuse me. Second digit. Okay, second digit indicates a modification to a specific alloy, unless it's a 0. If it's a 0, like you see there, 5083, that is the original 83 alloy when it was registered. 5183 was a modification to alloy 5083. Same as 4043 was the original alloy registered for 43. 4943 is a modification to 4043. So the second digit indicates a modification unless it's 0, then it's the original alloy. Okay. The last 2 digits in the 4-digit numbering system don't mean anything. They're just an arbitrary number assigned by the Aluminum Association in order to track the alloy in the register. However, there's one exception, and that's the 1000 series alloys, right? One exception, 1000 series alloys. So what is that exception? Okay. In the 1000 series, the last 2 digits indicate the purity of the alloy above 99%, okay? And the examples here, we see 1100 is 99.00, right? 00. 1188 is 99.88% pure. 1050, 99.50%, 50, right? Percent pure. So that's the only time those last 2 digits mean anything. Okay, just an example here, 5183, I know that it's a filler alloy actually. It's a modification. Okay, so it's a magnesium alloy, it's 5000 series. It's a modification to alloy 5083, and it was actually made as a filler alloy for 5083 by adding some grain refiners. It's the specific alloy number of 83 of the 5000 series. Okay, simple. All right, filler, we're getting I don't know. I'm going to go through this. Filler metal selection. First off, anyway, just want to tell you quickly, it says breaking news here. You may or may not have heard of a document called AWSA 510. It is the AWS specification for the classification of aluminum filler alloys, right? We have just written, I'm the chair of this committee, and we have just written, and it's just been published. They tell me by the end of this month, this will be for sale. The 2021 edition will be for sale. And it's big news because it's the first time ever that it's included the minimum tensile strength of filler material for aluminum filler alloys. Never been done before. It's always been based on chemistry only. Now it's chemistry and minimum tensile. So we've added a couple of tables that requires tensile testing and provides the minimum strength requirements, and there they are. And what you'll see here, just for your interest, we have 4043 coming in at 24 KSI. This is the minimum guaranteed strength. It's not the typical, it's a little bit below the typical. But the interesting thing here is we see 4943, which is the new 4000 series, and it comes in at 30 KSI. So 2430, substantially higher. And again, this is not the typical, as it is the minimum. The typical would be slightly higher. So all these figures here have been around for a long, long time, except the 4943, which we just got together by testing. Okay. So there you go. Let's go. In terms of filler alloy selection, I don't know. We have a filler alloy selection chart that's very readily available here in the States. as part of a brochure that we have, and I don't know how accessible that is in India. However, this certainly should be. This is a Hobart app. You could go to the App Store and you can download this Hobart filler metal selection app. And it has a section on all materials, but the aluminum section is great. And it does a lot of other things just to select the filler alloys. But if you're not aware of this, you may want to acquire it through the App Store. Moving on. Yeah, that's our 40-page technical brochure. And as I say, I don't know how easy it is to get it to you guys in India, but we could always try. In it, on the back page, there's a 3-page fold-out, which is the filler alloy selection chart, which is really good. But all the same information is in the app. Okay. And this is what the chart looks like. It has all the base alloy, it has all the base alloys here and here, and it has all the filler alloys down here and across here. All right. Let's see. Let's just go through and explain how this works. All right, so I said earlier, and I'll just reconfirm that the selection of filler alloy for aluminum is different than steel. And just to give you an idea on what I'm talking about, these are the considerations. Crack sensitivity is really important. Certain alloys are very crack sensitive, and if you don't use the right filler alloy, they will crack. Strength of the filler alloys is different significantly in some instances. You might be able to use that filler for that base material, but the strength could be quite substantially different. And if you choose the wrong one, you might not pass the transverse tensile test. Ductility, yeah, big difference. Typically, the 4000 series lack ductility. They have lower ductility than the 5000 series. Corrosion resistance, absolutely. There are differences in filler alloys, and we have ratings for them. Elevated temperature service, critical. There are only certain filler alloys that can be used at temperatures above 150 degrees Fahrenheit. If you choose the wrong one, you're going to get into stress corrosion, cracking problems. Color match after anodizing, big deal. If you're going to anodize a cosmetic component and you use the wrong filler alloy, all the welds are going to go black. Post-weld heat treatment, yeah. Some filler alloys will respond favorably to post-weld heat treatment. Others will not. In fact, it would be a bad thing to use some filler alloys and then post-weld heat treatment. And then toughness, certainly. There are differences in toughness between the filler alloys. So all of these ratings are covered in the filler alloy selection chart. Hope I'm not running out of time. And that's just essentially how it works. Does somebody want to tell me whether I need to speed up or am I running out of time? Or because I could go for about another 10 or 15 minutes if it works for you guys.
It's going good. It's going good, Tony. We're good for 15 minutes. You can take 20 if you want. People are really engrossed. So you can take your time.
All right, then I'll carry on. All right, so what we've got here, it's just showing you how you use the chart, essentially. We've got the base house. In this case, we've got 6061 welded to 6061, and we do this thing here, and we go to this circle here, and this gives us all the filler alloys that you can use for welding 6061. And I believe there's 7 of them or 8 of them. 1, 2, 3, 4, 5, 6, 7. There are 7 filler alloys listed that you can choose any of them. Any of them are weld 6061. However, if dependent on your application, you may choose one of these over the other, most definitely. For instance, if you're going to anodize, you would not choose 4043 because the weld would go black. You would use 5356. If you are going to use this component at temperature, right, above 100, and that's 150 degrees Fahrenheit in service, you would not use 5356 because it's got more than 3% magnesium. And you could run into sensitization problems and stress corrosion cracking. So there's lots of issues here that you need to understand. And we could talk at least an hour probably just on filler alloy selection. But I want to give you an overview so you can dig deeper yourself. It is different. You've got to be careful and look out for these differences. Here's an example, and it's a temperature example, which is a good one. We've got some 5454 base material, and I know this is a 3% mag maximum base alloy, which is typically designed to be used at temperature, elevated temperature. It's going to be used as a support bracket in an industrial heater, and it's going to be subjected to 250 degrees Fahrenheit for prolonged periods. Okay. Okay, so which filler alloy would we use? It's 5454 to 5454, and it shows we've got 1, 2, 3, 4, 5 different. You could weld it with any of those, right? However, we've got this temperature issue, so we need to look up the temperature. And if we look at the temperature, we'll see there's only one filler alloy we can use. All the others, all these are blank, 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 blank. That means don't use it. Unless it's got a rating, do not use it if that variable is important. So in this case, temperature is most important, and there's only one filler alloy that has a rating for welding this base material to this base material for temperature applications, and it is 5554. And 5554 was designed specifically for welding 5454, and it has a maximum amount of 3% magnesium, so it doesn't become subjected to stress corrosion cracking or sensitization. All right, that's just one example of many issues that are related to these variables and how they can affect the filler alloy selection. So if somebody calls me and he says, I've got this base alloy and I want to weld it to this base alloy, what filler should I use? My answer to that question is always, how the hell do I know? I can't tell you. I have no idea what filler alloy to use unless you tell me what the component is expected to do. How is it expected to perform? What is the environment? Are you looking for strength? Is it used at temperature? Are you going to anodize? Do you need really good ductility because you're going to form the material after it's welded? Is toughness critical? So unless you know that, you cannot select the most appropriate filler alloy. And that's why, as I said earlier, filler alloy selection for aluminum is very, very different than most other materials. Hope I got that one across. All right, and this is a list, and it's something we publish in our book, and it's kind of like, I don't know, what would you call it? Just a do and don't list, good practice. So base material, it says less than 3% mag, you can use 4,000 or 5,000. Good anodizing color match for 6,000, use the 5,000. Higher ductility and toughness, 5,000 over 4,000. Elevated temperature, you can use 4,000 or 5554, which was designed for that. So it goes on and on. So yeah, this is all based on what you would find if you were to look on the filler alloy selection chart. Right, a little bit about weld discontinuities. And I want to, I said I chose two. I mean, most of the weld discontinuities are the same in aluminum as they are for other materials, but two of them stand out to me because they are different in some respects. So I chose porosity and cracking, and let's take a look at those. First of all, what is a discontinuity? And I always have this slide at the beginning of this section, because a lot of people talk about defects like every discontinuity is a defect. Well, they're not. It isn't. Every defect is a discontinuity, but every discontinuity is certainly not a defect. It has to be outside an acceptance criteria. So my advice to people is tend to refer to porosity and cracking and undercut and all these things as discontinuities rather than defects, because they may or may not be defects, because you may or may not know what the acceptance criteria is. So it's advisable, particularly if you're writing a report. So just my advice. That's all. All right, so we're going to talk about weld cracking and porosity. So porosity. Cavity type discontinuity, we all know what porosity is, right? It's caused by gas entrapment during solidification. And cracking, yeah, right, fracture type discontinuity, and that's the definition, the AWS definition, the height to depth ratio and so on. So we all know what a weld crack is. Moving on from there. All right, so Porosity, again, cavity type discontinuity, and it's formed by hydrogen gas. This is really important, and which is entrapped during solidification. It's all about hydrogen in aluminum. Aluminum has a high affinity for hydrogen when it's in its molten condition. All right. So if someone calls me and says, I've got a porosity problem, I say, well, okay, there is no quick fix for this, but you need to understand, in order to find out where it's coming from, that you have a source of hydrogen near your weld, right? Now it's up to you to find out where that hydrogen is coming from. All right. So it can come from I've listed 3 areas here of concern, and these are the typical 3 areas that you need to look at. Hydrocarbons is the first one. So that's any form of contamination, usually on the surface of the plate, but can be on the surface of the wire, right? Like oil, grease, paint, or any type of contaminant that might be on the surface that may have hydrocarbons in it can cause porosity. The next one is hydrated aluminum oxide. Okay, aluminum oxide, I said it's a strange beast, right? It does a number of things, and one of them is that it can absorb moisture and it can become hydrated. All right, if you weld over a hydrated aluminum oxide, it will release that hydrogen during welding, and that will cause porosity. So you have to remove any hydrated aluminum oxide from the surface of the plate, and you have to make sure that your wire is not contaminated by moisture, right? And then moisture generally. Moisture can be in the atmosphere. If you're working in a humid environment and you have changes in temperature, you cross dew points and you can get condensation on your wire and your plate. You can have moisture in your shielding gas, right? You can get moisture from your cooling system if you're using water-cooled equipment and you've got any leaks, all right? And other external sources like compressed air, people blowing compressed air on the surface of the plate and it having moisture in it, and oil in it for that matter, can cause porosity. Okay. This is a classic solubility of hydrogen in aluminum. As you can see at room temperature, it doesn't want anything to do with hydrogen, but as we get to its melting point, all of a sudden, at its melting point, 1220, its capacity to absorb hydrogen goes up tremendously and increases and keeps going up as the temperature gets higher. So we're operating at temperatures around here somewhere, aren't we? 3,000 degrees, I don't know. Doesn't really matter. When we melt aluminum, it wants to suck in hydrogen. If there's any around the weld in various forms, it's going to take it on board. Then as the weld solidifies, it can't get out quick enough and it causes those bubbles right in the weld. And this is what they look like. If you don't have X-ray capabilities and you want to check a groove weld, you can do a nick break test. You can cut a slice of the weld, you can nick it and you can break it and you can look in the inside of it. These little tiny dots are micro porosity, which is very, very difficult to get rid of, but very, very acceptable usually in codes and standards because you don't count porosity over a certain size. So this tiny micro porosity is usually acceptable, but these big hunking porosity here is not. Each one of those would need to be counted, and I'll tell you now that this would probably fail, certainly A510 requirements and probably D1 too. So yeah. Here we see porosity in a cross section of a fillet weld. Again, it's guaranteed this porosity is formed by hydrogen. Where the hydrogen comes from is what you have to find out and eliminate. This is an interesting slide, and it's a bit misleading, but it's interesting. Is porosity a really nasty discontinuity? Well, in my opinion, not really. It's a pain in the ass, and it's difficult to get rid of at times. But does it reduce the strength of the weld tremendously? No, nowhere near as much as a crack or incomplete fusion. And in fact, this is what this is showing. It's telling us here that if we weld 6061 with 5356, we can actually remove 40% of the weld, nearly 30-some% of the weld, right? So 1/3 of the weld can be removed before we drop down to below the design strength of the weldment. And that sounds bizarre, right? What 1/3 of the weld can be missing and it still meet minimum tensiles? Well, really, if you look at the strength of the base material and the filler alloy, minimum tensile 24, and then you've got 53, 56, which has got about 40 KSI. You know, you can remove a lot of this filler alloy before you drop down to that strength. So it's a bit misleading. But anyway, moving on. So potential sources: welding in drafty conditions, blowing away your shielding gas is going to contaminate the weld. Excessive spatter buildup inside the nozzle, restricting gas flow. Incorrect standoff distance. All these are starving the weld from shielding, which contaminates from the atmosphere. Establishing and maintaining correct shielding gas flow rate. Contamination of plate surface, we mentioned. Exhaust contamination with compressed air, absolutely. Quality and cleanliness of aluminum weld wire, absolutely. All aluminum weld wire is not created equal. And you've got to store it correctly. And once you screw it up, it's screwed up. There's nothing you can do about it. You ain't going to get X-ray quality welds after you've subjected that weld wire to changes in fluctuations in temperature and humidity and had condense on the surface of it. You will have hydrated oxide and you will not get crystal clear welds, and you X-ray them. Anti-spatter compounds, be careful. Not recommended for aluminum. Water leaks, obviously. Inadequate pure shielding gas, not typically a problem, but it can happen. Imperfection in the gas delivery line happens all the time. Bulk gas systems with leaks can be a major headache. Condensation on plate surfaces, absolutely. Hydrated aluminum oxide, absolutely. Cutting fluids and saw blade lubricants, yeah. You can cut aluminum dry. You don't have to use cutting fluids and lubricants. So whenever you get a chance, cut it dry. But if you do use them, make sure you remove them. And that's not always easy. Dew points, I said earlier, if you're working in humid environments, and you guys certainly do over there, then you've got to be careful about fluctuations in temperature. Small changes in temperature can cause moisture, right? And give you an idea, if we're looking at relative humidity in the 80s and 90s, very small changes in temperature between the atmosphere and the metal are necessary in order to get condensate. And you'll get moisture appearing in, even if you don't see it, on the surface of your wire and on your plate. So be aware. All right, we'll go through all these. All right, moisture removal, degreasing, wire brushing. So pre-cleaning, if you want X-ray quality welds, not high quality welds, you really need to take cleaning, pre-cleaning, really, really seriously. The best people out there that are turning out the best aluminum welds pay much attention to the pre-cleaning methods, storage and pre-cleaning. And usually it's moisture removal, degreasing, and wire brushing in that order. Correct storage of base metals, appropriate removal of oxides. Okay. The amount of cleaning, I said earlier, it's determined by the end product, obviously. If you're building a bicycle rack or something that's not safety critical, you don't have to worry about cleaning the hell out of it. But if you're building something that is safety critical, like a heat exchanger or LNG tanker, ballistic armor plating, or you really need to be paying attention to this. This is a good solvent we use here in the States, made by a company called LPS, called Zero Tri. You can spray it on the surface of the material or on a paper towel is what we normally use, and wipe down the surface, and that will get rid of hydrocarbons. And that is the first thing you do before you wire brush. You will always degrease before you wire brush. Otherwise, you can take the contaminants on the surface and you can put them into the subsurface if you haven't removed them when you wire brush, and also contaminate your wire brush. All right. The other thing, if you're going to power brush, be careful, don't overdo it. At light pressure, low revs per minute, because you can actually churn that oxide and embed it into the surface of the material. So be careful. Be careful with compressed air also, because it can cause a lot of contamination. It's not usually very clean. All right, cracking. All right, let's go back one. Yeah. All right. But all cracking in aluminum is hot cracking, and we see it under a lot of different names. Well bead cracking is often called solidification. Thermal cut edge cracking, I'll talk about, which is also solidification. Fusion zone cracking is often referred to as liquefaction cracking, and there's precipitation cracking, and we get stress cracking. If we subject the weld to more stress than it can actually stand during solidification, it's going to pull apart, and that happens quite a lot in aluminum. People don't understand it because you've got a lot of shrinkage, which gives a lot of stress. So let's move on a little bit. Okay. It's a high temperature cracking mechanism, all right? And it's mainly a function of how metal systems solidify. The next slide, okay. So I say this all the time, it's all about the chemistry. And that's why I said earlier, you really need to know the chemistry of the base alloy that you're welding before you even attempt to put a welding procedure together. Yeah, otherwise it's, as I said, blind leading the blind. You've got to know the chemistry because it can seriously affect the crack sensitivity. I stole this from someone who Chris knows very well, Gene Mathers. I know him, I like to call him a friend. Known him for a lot of years, he's retired. He's a TWI guy, and he wrote a book, and you'll see his book just now, actually, Welding of Aluminum and its Alloys. I stole this from him because I think he does a good job of explaining hot cracking, and I'm going to read it. Hot cracking is a welding problem that does not occur in pure metals. The addition of alloying elements to a pure metal can result in a number of different phases being formed during solidification. One particular phase is the lowest melting point composition of an alloy, known as its eutectic composition, which freezes at one specific temperature. It is this eutectic phase that can promote hot cracking. In most metals, this effect is caused by impurities. Sulfur in steel and nickel is a good example, where low melting point sulfide eutectics are formed. In aluminum, it is the deliberately added alloying elements that form a range of eutectics with freezing points substantially lower than the bulk metal. I think he did an excellent job in describing what's going on here. All aluminum alloys have a certain susceptibility to hot cracking because they're all alloyed, apart from pure aluminum, of course, but any of the alloys are susceptible, just varying degrees of susceptibility. So it's all about how the material goes from liquid to solid and what is left in these grain boundaries at the end of solidification. If we have these eutectics along the grain boundaries here, these low melting point components, then they tend to rip apart during solidification from the shrinkage stresses, and that's when we get hot cracking, all right? And this hot cracking phenomena has a standard flow, if you like. It starts off very low as we add alloying elements. Very low amounts of any alloying element usually have very low crack sensitivity. Then as we add more and more alloying elements, it increases and increases and increases, and it reaches a peak of crack sensitivity at a certain amount of alloying element. Then as we add more alloying element, it gets lower and lower and lower and lower and lower, okay? So the secret here is to prevent being around the peak of crack sensitivity in terms of alloying element addition. We need to either be on the left or on the right-hand side of the crack sensitivity curve. So these crack sensitivity curves were developed by Alcoa many years ago when they first started welding aluminum. And they were a well-kept secret, in my opinion, until recently. And I actually put them into welding aluminum theory and practice. They weren't in there, believe it or not. But anyway. Okay, so all aluminum alloys, I said this, are susceptible to some degree. It differs only by the degree. All right, cracking testing has been used to determine the crack sensitivity. So we're going to look at the crack sensitivity curves, and here they are. You'll find these published in a number of documents now, but they were very well hidden for many years for some reason. But anyway, so what we're looking at is 4 individual crack sensitivity curves here. We got silicon in aluminum, copper in aluminum, magnesium in aluminum, magnesium silicide, Mg2Si in aluminum. And we see the amount of those elements and how it affects the crack sensitivity. So if we look at the top one here, aluminum and silicon, we can see, and I'll tell you at 0.8%, just below 1%, 0.8% is the peak crack sensitivity of silicon in aluminum. So if you've got a piece of aluminum and you've got 0.8% silicon and you try welding it, chances are it's going to crack, right? Now, with copper, it ranges all the way from just above 1 all the way over here to about here, peaks around here. So anywhere between 1.5 to 3.5, you could run into crack sensitivity problems. So the copper alloys tend to have a wide range of crack sensitivity, and for that reason, sometimes somewhat difficult to weld. Aluminum magnesium peaks at around 1, just above 1%. Mag silicide, again, just around 1, just over 1%. Okay, so what does that all mean, to the welding engineer when he's designing welding procedures? Well, it means if you weld some base materials that are crack sensitive without adding filler alloy to compensate by changing the alloy structure and consequently its crack sensitivity, it will crack. And here we see the best example. This is a piece of 6061. The weld on the right was autogenous, no filler material, right? And you can do this, take a TIG torch, take a piece of 6061, put a real heavy bead down the plate with no filler alloy, and I'll guarantee it will crack, all right? Same plate, same welding process, 4043, or any filler metal for that, 4043, 4943, 5356. 4043 is a good example. Add some filler alloy, no cracks, same base material. Why? Well, we've changed the chemistry of the weld. This weld metal is now a mixture of the base and the filler alloy, and the filler alloy has changed the chemistry of the base and reduces the crack sensitivity. Okay, here, no, the base is crack sensitive. You weld it with no filler, it's going to crack. All right. Just a radiograph of the same. This is what we're talking about. 6061 base material has a crack sensitivity, has a mag silicide content of around here. So if we weld it without filler, it's going to crack. What we need to do is move this mag silicide, usually over here, by diluting it with another element to prevent the cracking. All right, some examples right there. Okay, that's the crack sensitivity curve. This is the reason there is no 6000 series filler alloys. If we had a 6061 filler alloy, every time we used it, it would crack. All right. Okay. So why does it not crack when we had the 4043? Well, as I said, we changed the chemistry, and we also have high silicon, which I told you earlier, reduces the shrinkage during the freezing. So 4000 series is very good to prevent cracking. All right, so what does this mean in reality? Well, okay, people call me sometimes and say, hey, I'm welding 6061 groove weld, and I'm welding it with 5356, and it keeps cracking. Okay, and I said, well, okay, what joint preparation? Well, I'm using a square edge joint prep. All right, and I said, well, put a V prep on there and try it and see what happens. Okay, this is what it's all about. If we have a square edge prep, we're looking at about 20% filler metal and 80% base material. That weld is going to be a composition of 20% filler, 80% base. If we put a prep on here, we change this ratio. We have now 60% filler, 40% base, which changes the chemistry. The chemistry of these welds is different, as you can see. right? 6061 base material has 1% magnesium. 5356 filler material has 5% magnesium. So if we take 20% of the filler metal, which is 5 mag, 80% of the base material, which is 1 mag, we do the calculation, it comes out at 1.8% magnesium in that weld. So you've got aluminum here. This weld, this molten weld here is made up of aluminum with 1.8% magnesium, or thereabouts, very close. Now we prep, we put this prep, we now change this to 60% filler, so 60% of 5% mag and 40% of 1% mag. We end up with 3.4% magnesium in this weld, right? So this weld has 1.8% magnesium in aluminum. This one has 3.4% magnesium in aluminum. Which one's going to be most crack sensitive? 1.8, 3.4, 1.8, 3.4. Okay. 1.8 is almost at the peak crack sensitivity. 3.4 drops the crack sensitivity all the way down here. So the probability of cracking when you use that V-prep is reduced substantially, all right? So on occasion, the guy will call me back and he'll thank me, but most times they don't. I don't hear from them. But I can guarantee that's going to resolve your problem. All right, some other cracking, under bead cracking. On the heat treatable alloys, if we overheat them, particularly in multi-pass welds, we can cause this intergranular cracking around, beyond the fusion line, right? Not uncommon. So we've got to watch our heat input. Now, this is cracking inside a 6000 series. We have a weld here that's deep, the penetration goes way back here. So we're getting this micro cracking on the inside of the weld. Crater cracking, aluminum. You've got to be really careful about buttoning up those craters. You've got to fill in those craters, otherwise you're going to get crater cracking. This is an odd one that a lot of people have never seen. If you are plasma cutting any of the 6000 series or any of the heat treatable alloys for that matter, the codes require that you remove 1/8 of an inch of that prep before you incorporate it in the weld. Because you're going to get these micro cracks across the surface of the weld. Nearly finished, guys. All right, so how do we prevent hot cracking? Hey, do everything I just told you. Avoid weld profiles that are excessively convex, and on and on and on. Use the filler alloy selection chart and check out the crack sensitivity. Oh, right, got to go through this quickly, just quickly. I hope everybody hasn't left already. All right. Couple of books that are available out there. This is the one I told you about, has the crack. I thought those crack sensitivity curves were so important, I put it on the front cover of the book. This is Aluminum Welding Theory and Practice, available through the Aluminum Association. If anybody asks me which one single book should I get about welding aluminum, I tell them this one. This is very useful if you're choosing materials. It's not a welding book, but it gives you all the strengths of all the different alloys and all the different tempers. That one you've seen already, it's the teal sheets. This one is the equivalent for castings. There's about, I think, 300 or more castings listed in here with the chemistries. It's called the pink sheets. This is the aluminum design manual. Again, very little in there about welding. It's purely about structural design. And that's Gene's book. Very good book, probably available through the TWI, I would imagine. That's my book, available through the AWS, Welding Aluminum Questions and Answers. Structural Welding Code Aluminum. I've been an advisor to this committee for many years. I was the vice chair for years. Very good book if you get your hands on it, and you're strong enough to pick it up. It's big, heavy, but it's got a really good section on welding in it, and a lot of other stuff. If you're just looking for physical metallurgy, you probably can't go any better than Hatch's book, Aluminum Properties and Physical Metallurgy. And that's it, guys. I'm sorry I went way over, and I hope everybody just left. Is
Not
anybody
at
there?
all. I think Tony, you've still got about a good fair 175 people on board. So we had about 190 most of the talk, and I think just a few of them would have had to push off at 7 o'clock in the evening here. But
Sure.
wonderful presentation, Tony. I think you just explained the chemistry fair out and made all of us understand the basics, and you just simplified it so well. It makes hell of a difference. I got to ask this because many people are asking for it. Would you be sharing the presentation?
Yeah, I think I can arrange that. Would I do that through Chris?
All right, so that would be great. If you could share it with Chris, Chris could email it to us, and then we would share
I don't
it with
know.
people who attended.
Whatever's the best way. I'll share it. Well, I could share it as a PDF. I think I probably shouldn't.
Yeah, that would be great. That would be great.
Yeah,
Share it as a PDF.
If you
I'll
do
make
it
it in a
to me, Tony, I can then sell it.
Yeah, I'll make it into a PDF and send it to Chris, and he can get it to all you guys.
That would be great. That would be great.
Yeah, and a lot of questions are waiting in the Q&A session. If you can take up few, that will be good.
Sure.
All right. So in the Q&A, we have first. Would you like to pick up from the Q&A, Tony? Would you want to just look at the Q&A?
How do I do that? Where are
Then
we?
there's a next to the
okay.
chat. There is a box called Q&A.
Thermal conductivity of aluminum is 5 times of steel. How do we compensate during welding with respect to preheat or using higher heat input? Yeah, absolutely. Good question. This first question is asking, how do we compensate during welding for this 5 times heat sink more than steel? Yeah, the way it's done, preheat is not the answer. I give an example. When I started in aluminum, I say about 25 years ago, specializing in aluminum, one of my first jobs was to qualify our Lloyd certification for a company called Elcotech, which then was probably the biggest aluminum filler alloy manufacturer in the world. And Lloyd's test was welding a 1-inch thick T-joint with the smallest and the largest size wire you wanted qualified. So we wanted 030 wire, right? 030 wire is our smallest wire. It's tiny. And you had to do a fillet weld in a 1-inch thick plate with no preheat, right? I thought it was impossible. I said, no way. There's no way in hell you have to get full root and full sidewall fusion.